To generate light through resistance, you force electricity through a narrow metal filament until the friction of the moving electrons generates heat. When standard mains voltage hits this electrical bottleneck, the temperature of the wire rapidly spikes to 2500 degrees Celsius. At 2500 degrees, steel liquefies, and most structural materials vaporize. It is a strictly hostile thermodynamic environment. An incandescent bulb is a specialized high-temperature resistor. Its primary engineering requirement is to prevent its own components from melting during operation. To function as a standard lighting source, the system must maintain a consistent output of 800 lumens. That light must remain stable, emit a warm color temperature of 2700 Kelvin, and project outward in a full 360-degree sphere. This polar plot maps the light distribution of a standard bulb. Casting this even 360-degree spread depends on an unobstructed optical path, ensuring no internal supports block the outward radiation. Delivering that uniform output while containing a 2500-degree core dictates the entire architecture of the bulb. To understand the design, we have to build the system from the inside out. The core of the system is the resistor itself, the filament. The technical specifications identify this filament as tungsten. This material is required because its melting point is high enough to survive continuous operation at 2500 degrees without liquefying. Heat is only the first variable. Operating at these temperatures introduces a secondary vulnerability, atmospheric oxygen. When metal is superheated in the presence of oxygen, it rapidly bonds with oxygen molecules in a reaction called oxidation. A hot tungsten wire exposed to open air essentially combusts. The metal becomes brittle and the circuit severs in a fraction of a second. Raw heat generation is useless without environmental isolation. The resistor must be physically shielded from the surrounding atmosphere. 19th century engineers addressed this by sealing the filament inside a glass envelope and pumping out the air to create a vacuum. This required borosilicate glass. Standard glass would shatter from the thermal shock radiating from the filament. Removing the oxygen stopped the combustion, but the vacuum environment triggered a different failure mode, tungsten sublimation. At extreme temperatures, tungsten atoms vibrate so violently they break free from the solid wire and drift away. These escaping atoms coat the inside of the glass, blackening the bulb. As the wire thins, it eventually loses its structural integrity and snaps. While a vacuum solves the chemical problem of oxidation, it causes rapid structural degradation of the metal. The modern solution to sublimation involves replacing the vacuum by pumping a gas back into the envelope. This gas must be strictly inert to prevent oxidation. Engineers use a mixture of argon and nitrogen because these gases do not react with the hot tungsten. Filling the bulb with these gases creates physical vapor pressure that presses inward against the filament. When a tungsten atom tries to evaporate, it collides with the dense gas molecules, which forces them back onto the surface of the wire. This pressure slows the evaporation process, extending the operational lifespan of the filament to roughly 1,000 hours. The interior of the bulb functions as an active, pressurized buffer zone, essential for the system's survival. Suspending a 2500-degree wire in the center of this gas chamber requires a specific mechanical framework. The material specification identifies molybdenum for the support wires. Molybdenum is used because it maintains its structural rigidity at extreme temperatures, where other metals would warp. The most vulnerable point is the base, where the electrical lead-in wires pass through the sealed soda-lime glass stem. Every material has a specific coefficient of thermal expansion, meaning they expand at different rates when heated. If the metal lead-in wire expands faster than the glass holding it, the resulting mechanical stress shatters the glass and breaks the seal. To prevent this, lead-in wires are made of a nickel-iron alloy with an expansion rate that matches soda-lime glass. They expand and contract in unison. Without this exact thermal matching at the base, the hermetic seal would shatter upon the first use, venting the inert gas and destroying the environment. The final assembly of the device reveals a sequentially integrated pressure vessel. Electrical current enters through the E27 screw base and insulated tip, traveling through the matched leads and supports to reach the core. This requires a chain of specific materials: nickel-iron leads, molybdenum supports, a tungsten resistor, and an argon-nitrogen atmosphere, all contained within a borosilicate shell. While the interior remains a pressurized 2500-degree environment, The exterior projects a steady glow for the end user,